Kleene's theorem says any regular language can be accepted by a finite automaton. Until now we have seen the finite automaton. We have also seen the NFA and NFA-Null. So finite automaton means we are talking about the DFA. So according to this theorem, this says that in any regular language, whatever you have the language, if it is regular, then you must have some finite automaton. So how you can prove this theorem actually? So we need to give the proof of this theorem. So how we can prove? This is part first of the Kleene's theorem. We have some basic regular language. Say this is the null, and the language have only one string which is null, and this is the empty set. There is no string in this language, and you can have the language like this, which contains only one string of length 1, where a is what? Where a belongs to alphabet. This a is the input symbol. So these are the three basic regular languages we have. Once we have the basic regular languages, then the regular languages are closed under the regular languages are closed under the operation operations. Which one? One is union, concatenation, and Kleene star. Okay, we have seen. So we have seen that any regular language, if you have the regular language, then their regular languages are closed under the operation union. Means if you have two regular languages and if you form a union of such regular language, then you will also have the regular language. Resulting language is also regular. If you have two regular languages and if you can make the concatenation, then the resulting language is also regular. Whenever you have some language and if you are going to make the Kleene star of that language, then this is also the regular. So basic regular language, we have the empty, which is in this language we don't have any word. Next we have the only one string, which is the null. Length of this string is 0, and every language which contains only the one input symbol, string contains only one input symbol taken from the alphabet, this is also the regular language. So we have the three basic regular language, and using these three basic regular language, you can make some complex regular language by using the operation union, concatenation, and Kleene star. So here actually you need to show that how you can construct the. So our target is what? We need to prove that for any given regular language, whatever you have the regular language, you have some finite automaton. Means if somebody gives you some complex regular language and you need to say that yes, we have the finite automaton for this language. So how you can construct the finite automaton for some complex regular languages? So we can start from the basic regular languages for construction. So you need to show actually, instead of, you may not be able to construct directly DFA, but if you are able to construct the NFA-Null, then you know that you can convert NFA-Null to the NFA, then you can use the algorithm for converting NFA to the DFA, finite automaton. So you need to just, if you can show at least that for any regular language you have some NFA-Nulls, then your proof will go through. So what you need actually to do is, you need to see what are the NFA-Nulls for these basic regular languages. So if you have the empty set, how how you can construct the NFA null for the empty language? You can see like this. You have the some state, say starting state is Q0. You have the starting state, and we have only, this is the only state in your NFA null. And see that we have not designated this as the final state. This means nothing you are going to accept, and hence this is the NFA null for the language empty. So we are going to construct the NFA with null transition for the basic regular language. How you can construct the NFA null for the language that contains only the null string? Similarly, you can construct, say you are in the initial state Q0. This is the initial state, and since it is going to accept only null string, you make this initial state as the final state. So this is the NFA null for the language which is accepting only the null string. Similarly, you can also construct the NFA null for accepting the language that contains only the string of length 1. So you can begin with some initial state. Say you are in the Q0. Okay. From Q0, you have some input A, and you are going to the state Q1. Since you are going to accept only the string of length 1, so this will be the final state. So this is the NFA null for the language. You have this, where A belongs to input symbol. So see, these are the basic regular languages, and corresponds to the basic regular languages we have the NFA nulls. Now, in order to prove the theorem which says that any regular language can be accepted by a finite automaton, you need to show that how you can construct the NFA nulls for the complex regular expression. So you can, you know that if you have the two regular languages, and if you are making the union of the two regular languages, then the resulting language is also regular. Hence, if you have the two FAs corresponds to the regular language, and if you are going to make the union of the two FA, then you can say that you are going to accept the union of the two languages. Similarly, you need to show that how you can concate the two finite automaton for obtaining the regular language that can be obtained by making the operation concatenation. You need to show that how you can make the Kleene star of the NFA null, so that you should be able to obtain the regular language that is the Kleene star of some given regular language. So you need to actually show how you are making the FA, how you can combine the FA for union operation, how you can combine the FA for the concatenation, and how you can make the Kleene star of the given NFA null. So, okay. So see, let us see, you are given the two FAs. We have, so this is the M1 machine, M1 for some given regular language. Now you can have the machine which is M2 over the same alphabet sigma. So you have the set of states, you have the input symbol. This is the initial state of the machine, say M2. Q2 is the initial state. Set of accepting state by A2, and transition function of the M2 is given by delta 2. So you have the two machines, M1 and M2. What you need actually, you can show that how you can make the union of these two machines, and you need to show that how you can make the concatenation of these two machines, and how you need to show actually how you can go for the Kleene star of either M1 or M2. So actually we don't know the M1 and M2 exactly what are the states. So as a notional, we can see that like, see, we have some, if you are going to make the union, we are considering for the case of union. So how you can assume that this is some FA, and this is assuming that this is the machine M1. And if this is the machine M1, then initial state of this machine is what? This is the Q1. So Q1 is the initial state of this machine we have. And say it may have one final state, or it can have more than one final state. Assuming that it has two final state, let we name the final state like A is the one final state of your machine, and another final state of this machine is, say for example, B. So you have the two final states in this machine. Similarly, you have the machine M2. You have the machine, say for example, M2. And in case of the M2, we know you have the initial state is Q2. This is the initial state. And assuming that it has the final state, like this is one final state in your machine, okay, and this is another final state of your machine. You can have just one final state, or you can have three final state. We don't worry, just a notional. So you are coming to such final state from somewhere. You are coming, okay, you're starting from the initial state. And here actually in your Q1, you have the initial state Q1, and it can contain any other states also. And assuming that A and B are also in the set Q1, because A and B, we assume that these are the final states. So we have given the name of the final state like A and B, and you may have any other states. Similarly, if this is the Q2, then you have in the Q2, you have the states like Q2 or something else. Then C and D also included in this set, because C and D are the final state. So this is the case. Now, question is that how we can construct the machine so that it should be the union of the two FA. So we need to construct the machine which is the union. U denotes the union of the two finite automaton. So let us say that QU is the number of states in the union machine. The machine is, you are making the union over the same alphabet, and we assume that QU is the initial state of the machine you are constructing for the union, and AU is the final states, and delta U is the transition. So actually you need to show how you are going to construct the MU. Means you need to first identify the number of states in MU, is QU. You have some initial state. You need to find out the final states, and you need to show how this union machine can make the transitions. So we have the two machines here. One is M1 and other one is the M2. So if you are going to make the union, then we are doing like this. We add one state here, and which is, say, the initial state of this machine. We start, instead of initial state of Q1 is the initial state of M1, Q2 initial state of M2. For making the union, we are adding one additional state, which is the QU, and this QU is actually the initial state of your union machine. So what you need, if you execute the string, if you go for this M1, means you are having the strings, you are having the sentence from the M1. If you are visiting this M2, then you have the sentences from M2. So for constructing the union, you can, from the initial state, you can transit to the Q1, and also you need to transit to the Q2. So now in case of the union machine, QU is the initial state, and from this initial state you need to transit to the Q1, initial state of the M1, and by making the null transition, and by making the null transition also you need to transit from QU to initial state of the second machine. So this is what we have seen the construction of the union machine. So if you start from the initial state QU, if machine can visit to the Q1 and you know that you have the null transition, means without consuming input, you can go to this place or you can go to this place. Once you are going to the initial state of M1, means you are accepting the language for the M1 corresponds to the M1. If you are going to the Q2, means you are taking the accepting the sentences of the which are in the language L2. So see, this is the in this union machine. You have in this is the way you have formed the union of the two finite automaton. So if this is you have the M1 and this M1 is accepting the L1, which is the regular language. This is the M2, which is going to accept the regular language L2, and you are making the union, means you have now L1, you have now L1 union L2. So this machine, this is the language accepted by the machine MU. So language corresponds to the machine LU. MU is the union of the two regular languages. So what you have seen that what are the states in this machine? In MU, you have the QU. QU is what? Same number of states as you have in the M1, union Q2, and you are adding one state, which is the initial state, which is the QU. So this is the number of states in your union machine. Now, QU is the initial state, you have seen, and you have to define the accepting state of the union machine. So what are the accepting states? So this is same as the accepting states of the M1. So you can say that accepting state of the M1 is A1. So you have A1 union A2. So these are remains the accepting states. So you have now in the union machine, you have now the accepting state is A1 union A2. Now you need to show the transitions, delta U. What are the transitions here? You have not modified the transition in this machine. You have just added one states, and corresponds to that you have defined two transition, null transitions here. So whenever you are at the state QU, initial state, you have the null transition. What is the output? You are going to the set Q1, Q2. Means you can go to either Q1 or Q2. And if you are at the state QU, you have any input symbol A, then where you are going? You have not defined the transition. Our target is only to go to the initial states. So this is the empty. So you you are adding the transitions like this, and all other transitions you can, where A is what? For any A which is taken from the sigma. So you have not done the transition for the input symbols at the state QU. You just, your target is to go to the initial states of the two machines. Now you can define the transitions for any Q which is in, for any Q which belongs to the Q1 union Q2. The Q can be either in Q1 or it can be in the Q2. So you can, and you have some input, say A, and A can be either sigma, A can be from the sigma, or it can be from the null. So either A can be either null or A can be any input symbols. because you don't know. Here you may have some null transitions also, we don't know. So how you can define the transition? So you can say delta u, you are at the state q and you have the input a, you can define the transitions. And where q is what? Q can be either q1 or it can be in the q2. So how you can define the transition? So you can say this can be given as delta 1. Delta 1 is the transition for the machine M1. You are at the state Q and taking the input A. A can be null or A can be any symbol. If Q belongs to Q1. So if Q is in the Q1, then exactly you are making the transition according to the machine M1. You are not modifying. Now, if Q belongs to Q2, then you have to use the transition for the M2. So if Q belongs to Q2. So if Q is in the set of states of the second machine, then you are using the exact same transitions of the M2. You are not changing the transition. So this is the way you have shown that how you are going to construct the machine union. So for constructing the machine union, you have just added one state, and from that state, by making null transition, you are moving to the initial states of the two machines. And you are using the exactly same transitions. You are not changing the transitions for the machine M1 and M2. So once your machine starts with Q1, you are having the sentences from the M1. If it goes to the Q2, then you are having the sentences from the M2, and in this way you have formed the union of the two regular language. So if you have the two regular language, means you have the two finite automaton, and you have seen that how you are going to make the union of the two FAs. And this is the way you can construct the union of the two machine. So we have seen here how you are going for the union. Now you need to show that how you can make the concatenation of the two machines. So you have the machine. So we are going to construct the combining the two machines for the operation concatenation. We are going to construct the machine MC. C denotes the concatenation, and assuming that in this machine we have the set of states, we have the input symbol, we have the initial state of this machine, which we denote by writing the QC, we have the final state of this machine, which we denote by writing the AC, and transition function delta C. So we have it like this. So okay, so these are the two machines you have. You are going to make the concatenation. Now you see that in the operation concatenation, the order is important. What you want to concate. So this is, say for example, this M1 is accepting L1 and M2 is accepting L2. So whether you want to concate L1 L2 or L2 L1, if you have the L1 concatenation with L2, then the first part of the sentence will be from the language L1 and second part will be from the L2. If you reverse L2 L1, L2 and L1, then the first part will be from the language L2 and the next part of the sentence is from the language L1. So that's why in this case the order is very important. So just we need to show, let us see that we are going to concate L1. We need to obtain the machine for the L1 dot L2. So first you have the machine M1. So let us see, we have some machine here. So we are having some machine here. This is, and initial state of this machine is what? This is the Q1. Q1 is the initial state of the machine, and assuming that you have two final states here, which is one is A, okay, and other one is the B. And this is your machine M1. This is M1. Now we are going to make the concatenation. So we have other machine here. I am corresponds to the language L2. So you are having the machine this, and initial state of this machine is what? Q2 is the initial state we have seen. Okay. Now assuming that it has the two final state, one is C, this is one is C, and other one we can designate as, right, we can name the D. So D is the next final state of this machine, assuming. And we are going to make the concatenation. You are going to concate that machine M1 and M2. So this is corresponds to the L1 dot L2. So question is that how we can construct this, means you need to show that the what are the states in this machine QU. So QU actually we are going to construct, then once you go for the concatenation, then you know that whenever you are at the state A, which is the final state of the M1, means you have accepted the strings from the language L1. Now from this A, if you are going to the initial state of Q2, this means you are reading the next part of the string. So from here you can make the transition and you should go to the state Q2 and by making null transition. So whenever you are here, your machine may make the transition, may use the null transition, and it can go to the state Q2, which is the initial state of your machine M2. And once you begin from this, and whenever you are ending up at the state C or D, then you have the sentences for the L1 dot L2. Similarly, from B, you can go to the initial state of Q2, and this is also again making by the null transition. Now, you should not designate A and B as the final state here, because this is just first part of your concatenation, first part of the string, and here you are going to use the second part. Whenever your machine is ending up at C or D, then only your string is accepted for which is in the language L1 dot L2. So you don't require to make the final state for these two. You just say these are now, they are the normal state. They are non-final state here. And which is the initial state? You have to start from the Q1. So actually Q1 is equal to the QC. So QC initial state of the concatenation machine MQ, and QC is actually equal to the Q1. Means your machine is going to start from the state Q1. And this is the way you are going to concate. So what you have done here actually? What are the states QU? You are not going to add any states, and hence you can say that Q1 union Q2, these are the states in the machine QU. Now initial state, so you have the QC is the initial state of this machine, and QC is actually equal to what? This is the Q1. The Q1 becomes the initial state of this machine. Your machine starts from the Q1 and it is going to ending up to the C or D, then only you are going to accept the language. So philosophy says that whenever you are in the final state of the machine, first machine, from that you may wish to go for the next part, and hence by making the null transition you can go for start from the initial state. And once you start from the initial state, going to the final states of the second machine means you are accepting the sentences from the language L1 dot L2. So you have seen what are the final states now. So in case of the concatenation, you have the final state. Which are the final state now? You have the AC is equal to A2. And A2 is the final state of the second machine. Only these are the final state. Once you are going to make the concatenation, then the only final state is the final state of the machine M2. Now you have to see the transitions, how transitions are going. So see, you are not changing the transitions. you are not going to change the transition. What you are going to add? So you can say for any q which belongs to either state in either set q1 or it can be q2 okay, and q should not belongs to the a1. So what we are doing here, we assume that q is from any state q1 or q2, but q should not be in the a1. Means whenever you have this set q1 union q2 minus a1, we are excluding these two states, these two final state a and b of the first machine. And a can be what? A can be either taken from the sigma or it can be null string. Then you can define the transitions, or you can define the transition. So delta c, not u. So you have delta c means concatenation. So you are in the state q and you have input a. A can be null also and a can be any input symbol. So how you can you can make the transitions here for this case. So you can see you are not changing the transitions, means you have the same transition whatever in M1 or M2. So you can also say that this is same as delta 1 from the Q and you have the A. If Q belongs to Q1 and you are using the transition delta 2 from the state for the input A, if A belongs to Q2. So if Q belongs to Q1, you are using the transitions for the Q1, and if Q belongs to Q2, then you are just using the transition of the machine Q2. So delta 2 is the transition of the M2. Now see, here this Q does not contain the elements of the A1. So for Q which belongs to A1, okay, and A belongs to either sigma union null. So you have to see the transitions. So what you can say, you can define like this. So you have concate delta C, you are at the state Q and you have the input A. So see, now Q is any one of the states, either A or B, which was the final state of the first machine. So how you can give the transitions? So you can say this is same as the transition in the machine M delta 1, because this is the machine M1, and for the state at the state Q means either A or B, and for the input either input symbol A or you have the null. So you have the exactly the same transitions, and since you are adding the two null transitions also, then you can say that if you are at the Q and you have the input A, if you have the input A, then you are going to the state exactly making the same transitions of the delta 1. So delta 1 QA. So you can say here this if A belongs to sigma. Okay, so if A belongs to sigma, then from A and B you are making the same transitions of the machine. So you don't have any delta 1 is QA, whatever. Now, otherwise, you are going to say that QA union, what are you are going to add? You are going to add the transitions, which is say Q2. If A is equal to null. So if A is equal to null, then if you are at the state Q, Q can be either A or B. If you are at the SIF, if you are at the state A and you have the null transition, so you may have earlier some null transitions. So whatever you have the null transition earlier, delta 1 QA, this may be empty if you don't have any null transition, empty. But from the state this, you have the null transition which goes to the state Q. So from you are in the state A and you have, if for the null transition, you can go to Q2 and you may go to some other places also. So if you have the transitions earlier, this may be empty also, but you may have some other, you may go to the, if A is null, then you may have the null transition and you might be going to some other places, then making the union of Q2 because you are also going to the state Q2. Similarly, if you are at the B, then whatever you have the null transitions here, you are going for the null transition, you may be going some states union Q2 because from here you are going to the Q2. So these are the only transitions in your machine. Okay. So now you have seen that how you can make the concatenation. So for making the concatenation, you have shown that how you are going to construct the union means states, which one is the initial state, what are the final state, and how you can define the transitions. So these are the transitions of your concatenation machine. So now you have learned that how we can go for the concatenation of the two machines. So how you can make the Kleene star? You can make the Kleene star, say this is the language, you can make the Kleene star of this L1 or you can make the Kleene star of L2. So you need to show that how you can go for the Kleene star of the L1 means you need to show that for obtaining the Kleene star, once you have the regular language L1 and if you go for the Kleene star operation, then the resulting language, this is also the regular and this is also the regular language if you are going for the Kleene star operation. So now M1 is corresponds to the L1 means language L1 is accepted by the machine M1. If you want to show that you want to make the Kleene star of language L1, means you need to show that how you are going to make the Kleene star of the machine M1 so that it should exactly accept the language L1 Kleene star. So let us we denote the machine by writing the MK. K stands for the Kleene star. So you have the set of states. Let Qk, we have the input symbol, we have the initial state, say Qk is the initial state, accepting state, set of final states, you have the AK, and finally you have the transition function, say delta K. So you can make the Kleene star of any one machine. Let us see, we are going to make the Kleene star for the M1. So here you have the Kleene star operation. How you are going to make the Kleene star? So this is M1. This may be okay M1. So this is M1 and means if this is M1, you have the initial state and you have the final states. Assuming that we have two final states, maybe you can say you have the A. This is one final state. You can have the B, which is the other final state. Okay. So your machine starts from the Q1, and it goes to the A and B. So our target is to make this machine as the Kleene star operation. So for that, actually, you need to add one more state, which is the initial state of MK. you can see. So we have added one state which is qk, and qk is the initial state of your machine, which is the empty. Now what you need to do, from the qk you go to the state q1, means this is the initial state of your machine m1. So you have the m1, this is the initial state, by making the null transition. And now since you are going for the clean star operation, so you can make this state as the final state. So this initial state becomes the final state also, and from this state you are going to the q1. So what actually we are going to do in case of the concatenation, we are repeating. You have the accepted the first part, say x1, assuming that x1, x2, x3 all belongs to the L1. Then what we are going to do? So if you go for the clean star operation, if L1 clean star, it means you are forming x1, x2 like this. This can be one string, or x1, x2, x3. This is also one string. So how you are going to, once you are going to read x1, then once you start from the initial state of the m1, and on reading the input x1, you must be at any one of these states. Your machine must end up with either any one of the final states, either A or B. So once you are at the final state A and B, then again you have to start from the beginning for reading the next strings. So you are concatenating with previous one, means once you are here, then again you have to start from the initial state and you are going to read this. Similarly, if you go for the 3 times, so first for on reading x1, you will be any one of the state, either A or B. Then you have to restart from the beginning for reading the x2. Then you have to restart from the beginning for reading the x3. So if you go 3 times x's, then you are going to make the strings like this. So that's why from this state, once you are at this state, means you have accepted, and then you can repeat, and means you have to go for the beginning. So now this will not be the final state. Okay, so you just say here A, this was the final state of the machine M1. So once you are A, this was the final state of your machine M1. From A, you have to go to the initial state by making the null transition. And if you are at the final state in the B, you also go to the initial state by making the null transition. So see, whenever you are going to start from the Q1, you are ending up with the final states A or B. When you are at the B, you can begin again, you can start. So from A, you can move to the QK, and QK is the initial state. And if you are going to end up, if you just read the 2 substrings 2 times, then you can just end up. Or if you want to wish to go for more number of times concatenation, means you are accessing, then by using the null transition, you can again start from the beginning. So from this final state, you have to go to the QK, and from this final state also, you have to go to the QK by making the null transition. So see that for making the concatenation for making the clean star of the given machine, you have to add one more extra state. So this is required actually. The new state you need to add. Sometimes it may be possible that the Q1 can be the initial state, and you can make the initial state as the final state, and from here you can go to the, but for some language it may be the problem. So once you are going to make the initial state, this Q1 as the final state, then like this. You have seen the machine Q1 and you say 0, and for the case of 1 you are going to some other state, say Q2. For the 0 you are going to the state, say for example Q3, and if Q3 is the final state, so this machine is what this is just for accepting the string that ends in 10. You can show other transitions here. So if you don't add the initial state, then there will be problem actually, because if you are going to make this as the initial state, and from this final state, this will not be the final state now, and from here if you go to the initial state by making the null transition, and since this is the initial state, this means 000 will also be in the language, because once somebody gives you 000, then your machine is going to end up with the Q1, and you say that okay, this is in the language, but actually once you go for the concatenation, that string ends in 10, then again you will find the string ends in 10. You are going to make the concatenation of every string that ends in 10. So this is not in the language. That's why you have to add here one more extra additional initial state you need to add for the safe side, so that once you are at the final state, you just go to the initial state, and hence this is the final state. So so now actually what you need to show, what you have done here actually, what qk is there, qk is what, so qk is what, qk is same as q1 union, you have added one more state which is the initial state qk. So this qk will has q1 union qk. Now you can give the transitions, and final state is what, so you have the ak is the final state in the concatenation, and this is actually what, this is equal to the qk. So ak is actually initial state is the final state now, and then you have seen the initial state. Initial state is what, qk is the initial state you have, and you have seen that number of states, you have seen that set of accepting state. Now you see the transition function delta k. So whenever you are at the initial state, which is the qk, if you are at the qk and you have the input null, so where you are going, whenever you are at the qk, input is null, you are going to the state q1. Whenever you are at the qk, sorry, whenever you are at the state qk, and from and you are receiving some input a, then where you are going, you have now shown the transitions, and this is the empty for every a which is in the sigma. So for every a which belongs to the sigma, you have not shown the transition from the initial state, and hence this is empty. Now for any q, which are in the set, which belongs to the set q1 minus a1. This means what? So we are going to consider only the non-final states, and you have a can be either sigma union null. Okay, so how you can define the transitions? So delta k, if you are at the state q and you have the input a can be null also, or a can be any symbol. So we are not modifying the transitions of this machine. So this is exactly same as the transition of the machine. You have delta 1 and this. This is the same. So for every q which is in the q1 minus a1, which are not the finite state except a and b, because these was the finite state except a and b, the transitions are as it is. When for any q which is in the final states, so for any q which belongs to the final state, you have to show the transitions delta k. You are at the q and you have the input a, and here you have the a can be either sigma or you can have it null. So a can be either input symbol or a can be either null. So whenever you are at the delta k, whenever you are at the state q, how you are going to make the transition in the concatenation machine, and q belongs to the a1, means q is one of, will be some finite state. So you can say, you can give the transition like this, okay, like that. So delta 1, you are at the state q and you have the, exactly you are going to make the same transitions as the machine q1, as the delta 1 is going to make if a belongs to the input. Otherwise, what you are going to do, you are using the transition for the delta 1, means machine 1, and you are at the q, and for the case of null, so here you don't require to mention here union, just like, okay, or no problem, union null, okay. Now see, since you have written already a, so delta q k q a, if a is, if a is null, then what are you going to do? You are in some state q, you might have some null transitions, maybe empty also, then you are going to also add the states. Which states you are going to add? You are going to add the state qk if a is equal to null. So if a is equal to null, then if you are at the state a or b, if you have the state a, you may have some other null transitions or you may not have the null transitions. Okay. If you don't have null transition, then this is the empty, or if you have the null transition, you may go to somewhere. So this will output where you can go from the machine M1. Whenever you have the null transition, null, and you are at the final state where you are going, in addition to this, you have added one more transitions which goes to the initial state qk. That's why you have to add the qk. So you have now exactly, you have seen that if you have the two machines M1 and M2, how you can make the union, how you can go for the union, how you can go for the concatenation, okay, and how you can go for the Kleene star operation. So Kleene star. So if you have the two machines, then now you have seen that how you are going to make the union of the two machines, and how you are going to make the concatenation of the two machines, and how you can go for the Kleene star of some machine. And this is the way you are going to, this is the this is the way you can say that you have proved the theorems like any regular language can be accepted by finite automaton. Because for given any regular language, like if you have the regular language denoted by the regular expression like say 0 0 plus 1 Kleene star, and you have the 1 0, okay, this is the regular expression, and this regular expression denotes the regular language. So now see here actually you can corresponding regular language you can write like this 0 0 1 Kleene star, and then 10 Kleene star. So this is the regular language. So see, if you want to show that this is the regular language, then how you can prove? You can start from the basic regular language, which contains, which accept only the string 0, or which accept the string only 1. So starting from the basic regular language, you can show that how you can concate, how you can say one machine you have for the 0. Yeah. So how you can concate the machine to form the language 0 0 0. So this means that since you have seen that how you can concate the machines, so you start from the basic languages. So how you are going to obtain this regular expression? So you have already seen in the previous class that whenever you are in, whenever you have some regular expression like 0 0 or this, so how you can obtain? Starting from the basic regular expression 0, this is one regular expression, this is one regular expression, then you make the concatenation. So R1 concatenation with R2, you are going to form the R1 is corresponds to the 0 and R2 is same, so you can say R1 R1 R1, you are going to make the concatenation and you are going 0 0. Similarly, corresponds to 0, you have the NFA-Null, okay, and you are going to make the concatenation of same NFA-Null. You have the NFA-Null for accepting the language 1, then you have the NFA-Null for accepting the language 0 0, and you can make the union. This is the union, so you are going to make the union. So once you make the union, you will have the FA for the language 0 0 plus 1. Whenever you have the FA, NFA-Null, we are going to construct NFA-Null, and once you have the NFA-Null, you know that how you can go for the DFA. So you have the NFA-Null accepting this language, then how you can make the Kleene star to obtain the 0 0 plus 1 Kleene star. Then similarly, you can have the FA for the accepting 1, you have the FA for accepting 0, and you are going to make the concatenation and you are going to form the machine 1 0. Whenever you have the FA for the 1 0, you go for the Kleene star operation and you are going to obtain the Kleene star. So you have one FA accepting 0 0 plus 1 Kleene star and other is 1 0 Kleene star. You can concate the two machines to form the FA for accepting 0 0 plus 1 Kleene star and 1 0 Kleene star. So this is the way you can say that if the language is regular, means if language is regular, you have some regular expression, and you starting from the basic regular language, by making the operations union, Kleene star and concatenation, you are obtaining the complex regular language. Similarly, starting from the NFA-Null, from the basic regular language, you can obtain the FA for the complex regular languages. So this is the way, this is the proof of your Kleene's theorem part 1, which says that every regular language can be accepted by a finite automata.